This is the Earth Science Classroom. Welcome back to the channel. This video is on how we measure earthquakes, the scales we use to measure them, the energy, the amplitude, the intensity, the amount of energy released, and how we kind of both qualitative and quantitatively figure out how big these earthquakes are, both currently in the modern era, the 21st century, and historically as well. And this is in the seismology and earthquake playlist. So a little bit of history and the timeline of measuring earthquakes and in the subject or scientific discipline of seismology. We have here a timeline, and it goes from the left to the right, right being present day. And we can look at various dates and various significant discoveries and inventions in regards to measuring earthquakes and how we measure earthquakes. So we're going to put in one here is 1890, the year 1890. This is the year when the seismograph, which produced a seismogram, was invented. Now, the Chinese back in AD 120 did actually invent a machine that told people that earthquakes were occurring, besides obviously you feeling the earthquake personally. But the seismograph came around in 1890, and this was really a time when you can start to scientifically record an earthquake's movement and vibration of the earth. Now, the seismogram and seismograph is described in a different video, so please check that out. But we're going to look at the year 1890, so let's put this back in here. Now, before 1890, in any kind of historical earthquakes, before we had the ability to record and scientifically measure these earthquakes, there was evidence in structural buildings and the effects, the after effects of earthquakes on buildings, which would indicate a certain level of earthquake occurred in the past, but there was no real scientific detail or numerical value applied to these ancient earthquakes. However, post 1890, we get the Magni scale in 1902. Then we get the large San Andreas fault line, the large San Francisco earthquake of 1906, which measured a 7.8 on this scale, and that really developed and gave scientists opportunity to study earthquakes in much more detail right in California. Then came the Lawson report in 1908. Then we had the modified Magni scale. So we had the initial one in 1902 by the Italian seismologist Magni, and then it was modified in 1931 to adapt to modern day techniques or newer techniques. Then we had the Richter scale in 1935. Then from the Richter scale we had an advanced version of the moment magnitude scale in 1979, and that leads us to our present day. So we are currently using a moment magnitude scale for the most accurate and precise earthquake readings and earthquake measurements. So in order of the timeline, looking at the Magni scale, and this was first originated by an Italian seismologist called Giuseppe Magni in 1902. And this is a relative scale. It is based on the perception, observation, and human relative scale of damage and what constitutes damage and what, how much is broken during an earthquake. Now, this is extremely personal because someone could see a building and see a certain level and scale of damage, whereas another person right next to them could have a different opinion, different viewpoint, different perspective, different agenda, and say that damage is different. So this is a very well-used scale over the last 120 years. However, it is extremely variable and inaccurate in terms of a consistent scientific measurement. However, it was a first scale to be really invented. It goes from 0 to 12 and uses Roman numerals, as we see right here, to scale up the size and scale of the damage. So 0 would be very little damage and the earthquake is not felt by humans and there's very little damage to the built or natural environment, versus a 12, which would be catastrophic, cataclysmic, and everything is broken and destroyed. So it's observable damage, and it was modified in 1931 to be more exact, to get more of a consistent order of damage and what constitutes a level 5 versus level 12. And this was called the Modified Mercalli Index Scale, so MMI for short. And you can also use an isoseismic map to show the location of different levels of damage based on different variables, such as the population density, such as the building codes and designs and materials used to build each structure and house, which is varying on the country, even the area of the country, even the wealth of the country, because sometimes you can't afford the proper materials, the proper engineering codes and architects and scientists to build an earthquake-proof building versus one that's just going to fall down because it's cheaper. The rock type and the crustal rock and the foundation type, and also the distance to the epicenter. These will all be large variables of how the amount of damage could change depending on different earthquakes and locations. Also, if you are in an open environment, an open field with very little structures or no trees and nothing to fall down, nothing to break, you could have a massive earthquake. However, it would not register on the scale for Mercalli because nothing's broken. Things have to break, unfortunately, to be on the scale. So nothing's going to break, it wouldn't register on the scale. So that's why this Mercalli scale is not always the one that is scientifically used to measure earthquakes. And on the right here we have the scale going from 0 to 12 on the left axis and the y-axis. On the x-axis I have 3 different terms or variables: human perception, how we humans feel the earthquake and categorize it, to the physical and built environment, which is structures and buildings and houses, and also the term, like what do we assign, what word do we assign that level of earthquake on this scale. So from slight and weak up to violent and cataclysmic, and the 10, 11, 12 range. So after the Mercalli scale was modified in 1931, looking at the development of a more scientific, more quantitative measurement of earthquakes based on the physical attributes of the earthquake. So looking at the energy released, shown by the seismogram, which then shows amplitude and the max height of the shaking, and this relates closely to the seismic energy that's released from the earthquake, the energy. And this was formulated by Charles Richter in 1935, and it really measures the magnitude, the size. So you'll see magnitude when you look at a size of earthquake, you'll generally see an M in front of a number, let's say 7.0, and this is the magnitude. This is the Richter scale. And amplitude is that max height that you see on the seismogram, because when the earthquake shakes, the seismometer and the weighted pen on ball marks the vertical displacement of the energy, showing the amplitude, and this included with the time difference between the primary and secondary waves arriving at that seismometer at that location would give you the amplitude. And this, we can also look at how much energy is released and also see the distance. So we can get a lot of information from this scale. It is a logarithmic scale, which means that it goes in a log 10, so it's a 10-fold or 10 times increase with every number you increase in the scale. Or it's also a 10-fold decrease if you go down. So let's say you have a scale which this scale goes from 0 to 10. So if you go from 1 to 2, that would be a 10 times more motion, more ground motion. And it would equate to, each time you go up one number on the scale, it would equate to 31 times more energy released, which creates that 10-fold ground motion. So there's a lot more energy to create the movement of the ground. Obviously this depends on the geology of the ground, the depth of the earthquake, how long it lasts for, but this is a much more scientific and quantitative viewpoint of the earthquake, and easier to compare because it would work on consistent values of seismometers, giving consistent results throughout the whole world, so it's not based on perception, cultural differences, just like the Mercalli scale is. So on the right we have this scale. We have the magnitude from 0 to 10 over here, and it goes from, or anything below a 3, humans can't feel. Some animals can, but we can't. Anything above a 3, 3.5, 4, you get into the minor range of earthquakes, the size of energy release, the ground motion. And you get about 1 million earthquakes a year happening below a 3. Then you get 100,000 in 3 to 4, and it gets obviously a lot smaller, a lot less frequent the higher you go, up to 3 per year when you get to an 8 to a 9 magnitude, which is called a great earthquake. So there are certain earthquakes that happened around the world in different continents, and they're listed here. So the biggest one ever recorded by humans using this scale was in 1960. Now, because it happened in 1935, we could have experienced a lot larger earthquakes in the past. Because the scale wasn't invented until 1935, we have limited time. But since 1935, or since 1900, we have estimated that this one in Chile in 1960 is 9.5 is the biggest one we've experienced. Then you get Alaska in 64, 9.2, so that's North America and South America. Then you get Indonesia in 2004, Christmas Day, 9.1, causing the Sumatra huge tsunami, and that was the biggest in Asia ever recorded. Then you got Japan, very close, 2011, with the Fukushima nuclear power plant. That was 9.0, 9.0. That covers Asia. Then you got the Azores, or the Azores in Europe, which is 8.0, which is 1941. Then you've got Antarctica, which was around a 7.7 in Antarctica. And then you got Albert Rift in Africa, which is 1990, it's 7.1. And to finish off with Australia, or Australasia, looking at an earthquake in the Northern Territory in 88, which is a 6.6. So you get very large earthquakes pretty much in every continent, every part of the world. Now, it is based around the fault lines and tectonics, but they are definitely concentrated around the Ring of Fire, but you do get them in various continents. Now, the energy release, this is awesome. The average small earthquake that measures a 3 or below is a lightning bolt of energy. Then you get the average tornado is about 4.5 on the Richter scale, and you got to the first atomic bomb, which was dropped in Hiroshima in Japan during World War II. That was a 6 magnitude earthquake, and they happen 2,000 times a year. Then you get the largest nuclear test bomb ever, which was done by the USSR, which was an 8. And then you get Krakatoa, which is a VEI 6 eruption. That was a 9, or 8.5 to 9. So we get these comparable energy releases from these natural phenomena or human-induced events, but we have amazing amount of energy trapped in the crustal rock, just waiting to get out. And we get very large earthquakes, pretty much 3 to 20 times a year around all different areas of the world, and it's extremely dangerous, but also great to study as well. So between these two scales, the MMI, which was 1931, the Richter scale, which was 1935. Differences are obviously this is more quantitative, MMI is more observable, therefore qualitative, and definitely variable based on different areas of the world, different terms, different perceptions. This is based on a scale from 0 to 12, based on a scale from 0 to 10. However, the commonality is they are obviously both scales. They both measure the earthquakes. They both have a level of accuracy. They're both dependent on being there or having a seismometer around close enough to the epicenter to really get the true size and effect. So being there around, obviously if you're exactly in the location using the Mercalli scale or modified Mercalli intensity index or intensity scale, then you're looking at being in danger. But with a seismometer you can actively collect information without obviously being there. As with most scientific disciplines, seismology and earthquake readings and measurements are no exception. With increased time, education, experience, and knowledge gained over the course of the last 100 to 120 years, scientists have modified and developed the Richter scale to be more precise, to be more detailed on the depth of the earthquake, the types of waves, and looking at which amplitudes and which waves are more accurate based on the size and the scale and scope of the earthquake. So in 1979, they developed what's called the moment magnitude scale. This is an increased accuracy of measuring earthquakes. It's the measuring the magnitude. So it's a developed, more advanced Richter scale. Now, the modern day earthquake measurements are done in this. They are not done in the Richter. Not always, and they're definitely not done in the Magni. So looking at the different size of earthquakes, we can differentiate and be more detailed on certain properties of the rocks that shake during earthquakes. So how rigid the rock is, the size of the fault surface in the area, and also the amount and degree of movement, the displacement during the event can all give indications to a more accurate magnitude and relate to the amount of energy released. So we can also look at different variations of the earthquakes. We look at MW, which would be anything larger than the 5.5 and be very accurate for regional or larger areas. The ML, the way looking at more local, more close range readings and magnitudes of the earthquake, which is based on the Richter and Gutenberg scale back in the 1930s. The MO, M0, which is the size based on the size of the rupture or fault length, so that's the surface areas, MO, M0. MS, looking at the large and shallow earthquakes, the ones that are close to the surface but very large, over a 6. This would be a way to accurately see the size of the earthquake, because the Richter scale was very generic. This is becoming more detailed on different parts of the amplitude, different parts of the surface waves that go through the area. This is the Earth Science Classroom. Thank you for watching. I hope you enjoyed the content. Check out more videos on our channel, and don't forget to subscribe. Thank you again.